Hello everyone, this is Art Mazer. I'm happy to be here today. Today we're going to be presenting results from our final project. If you recall, my project is called a framework for designing recurrent neural networks with applications to dynamical systems. We'll be giving final results from the project today and also be looking toward what future work can be performed along these lines. But I get a sense that there's a little bit of a distraction going on here, and despite the presence of this very intelligent and handsome man in front of you, you are distracted by something. So what I'm going to do is get rid of the real distraction. Now we can concentrate on what is actually capturing your attention. And I believe it's this picture that's capturing your attention, so let's discuss this a little bit. Why would it capture your attention? Well, the human mind wants to make sense of things that are a little bit incomprehensible to it. If you look at the motion of this of these two lines here, it is quite erratic. It's unpredictable. You don't know what's going to happen next. It goes in one motion and then starts going another. There it's twirling right now, and now after twirling, it's just a completely different motion now. And it's your mind that wants to make sense out of something that seems to be random. Well, this actually is not a random process. This is from a dynamical system called the double pendulum. Just one pendulum stacked on the other, each with the ability to move around its pivot point. And as you can see, despite the fact that it's a system that is well described by a fairly simple set of equations, it produces extremely complicated motion that our mind wants to make sense of. So what's the relation between this and our project? Well, we're going to see that although it's difficult for us to make sense out of this and for us to predict where the pendulum's going to be in the future, we can train a neural network to do precisely that. Before we go on, let's look at some other motions of the pendulum. We'll start with the simple pendulum. Here we see one that's just swinging back and forth and back and forth. Its motion is far less complex than the double pendulum, which we just saw. This will put you to sleep. But there are things that we can do with the single pendulum. You'll notice that if we give it different starting conditions, what happens? The motion's a bit different. It's still periodic, going back and forth, but its velocity is different and its periodicity is different as well. And if we boost it up with a different set of initial conditions, what do we see? We see a different behavior altogether. We see the pendulum going in circles. It nearly stops at the top, almost not deciding which way it should go, and then completes its motion down around a circle and goes on again. So the simple pendulum, although a much simpler object than the double pendulum, can also behave differently. And we want our neural network to be able to capture all this different behavior. Let's look at the double pendulum again. So let's say goodbye to these guys. And look at the double pendulum. On the left, we see the double pendulum in a more simple mode than we saw before. The behavior is a lot less chaotic, somewhat predictable. I don't even know if it's periodic or not. It may be periodic, although I doubt it. Probably more quasi-periodic than periodic. It'll never return exactly to its same state. And here we see the double pendulum on the right that we'd seen before. This is one that's in complete chaos and extremely difficult to predict. So we'll want our neural network to be able to capture all these behaviors. And have a little bit of a background as to what a neural network is and what a convolution and recurrent neural network is as well. We see neural networks are gaining more popularity as they're able to address more and more complicated problems. One problem that we know that it's able to solve now is the driverless vehicle. We see a lot of vehicles out there from a lot of different companies. There's a Google driverless vehicle out there. We know that Elon Musk and Tesla is working with a driverless vehicle, Mercedes-Benz and many others, and they are using these recurrent neural networks for their processing. We've also seen neural networks have success in chess and in other games, Go, Wei Qi, which is an oriental version of chess. We see convolution networks working with image processing, able to classify thousands of images correctly. We know that there's automated voice processing, so when you call up on the telephone to some service and get a response on the other line that's not human, that those messages are being generated by a neural network. And we also have translation services that are being generated by neural networks. So how does a recurrent neural network work? What you see on the bottom is a graphic display here of a recurrent neural network. And you see a series of frames or cells that repeat one after another. In our case, these cells will represent different time frames. So we have a temporal sense to us. This is time frame 1, time frame 2, the initial time frame 1, time frame 2, etc., all the way down. So what happens with a recurrent neural network, you're trying to accomplish, is that you have an initial input into your neural net, and you're asking the neural network to process this, and this block represented by A, and then give an output, some output that you're hoping to see. Excuse me. Then we go on to the next time frame, and once again we're going to give an input. We're going to receive input from the previous computations as well, and from that we're going to give another output. The output should be consistent with what we're looking for. And then once again, we get another input from a data source. The neural net is going to process this new input along with any feed forward that it gets from the previous cell. And it's going to give us a new output. And this process continues on and on and on. So in our case, what are we looking for the inputs and outputs? Over here, we're going to give the initial state or the initial configuration of the pendulum, we're going to process that initial configuration and ask us to give out an expected or a predicted configuration at the next time frame. Okay, so that's what the H naught's going to be. Then we'll give it the actual configuration at the next time frame. So what we want is our prediction here, which is the prediction for what the configuration at the next time frame is going to be, to match the actual configuration that we're going to feed into the neural net. It's going to take some feedback from the previous cell. It's going to process this feedback here, and then it's going to give us a prediction for where we're going to be in the next time frame. This right here is going to be the input for where we actually are in the next time frame. So once again, this output, we're hoping, will match this input. So let's look at that a little bit more visually with our pendulums and see what the inputs and outputs are going to be. So what we're going to be feeding into the neural network is not a continuous trajectory of the pendulums as we saw before, but rather configurations after discrete points in time. The time difference between each time frame is the same. So what you're looking at here is what we'll be feeding in time frame by time frame by time frame. You'll see one configuration, and then we'll ask the neural network to go ahead and predict what the next configuration is. And then we'll feed in the new configuration, and once again ask the neural network to predict what the next configuration will be. So now let's discuss neural networks, and we'll start with talking about the design of a neural network and what it is. This graphic depicts a neural network, a 3-layer neural network. You can have many more layers, but we're just going to show 3 for the time being. This first level here is the input. This is actually external to the neural network. Your input is something that comes from the outside. It could be an image, it could be a chessboard, it could be a soundtrack. It depends what you're asking your neural network to do. In our case, the inputs are going to be the configurations of the pendulum along their trajectories. It takes the input and performs an operation on it, or it hits it with a function to get an intermediary result. This intermediary result is f of x, or a function applied to the input. Okay. Now you could stop right there, or you could continue. In this graphic, we're continuing, and we're getting another intermediary result by applying a new function we call g to the previous intermediary result. And finally, we take this intermediary result and apply a new function to it called h, and we call this the output, h of g of f of x. Once again, let me emphasize that for display purposes, I've only given 3 functions here, but you can have 1, 2, 3, or as many as you want before you cut from your input to your output. So what is the neural network? It's a nested sequences of functions that takes the input to the output. And each function within the sequence represents a layer in the network. Typically, the function in each layer is a linear operator followed by an activation function. The image above depicts a 3-layer network. So let's not get hung up on vocabulary, saying what a linear operator is and what an activation function is, but the important thing for us and in general for the neural networks, is that each function has many parameters, which allows one to fine-tune the results, and we'll discuss that in a moment. For the design of the RNN, each cell in the RNN contains the same nested sequence of functions. So this graphic picture right here, which gives layers in the neural network, is embedded into each of these cells of the RNN at this level A. This cell has the same architecture as this cell, as this cell, as this cell, and so on and so on. Let's talk about learning in a neural network. As I previously mentioned, there are thousands of parameters in the functions embedded in the neural network. My neural network, the one that we're using to follow the pendulum, has over 5,000, and this is considered small. So what do we want? We want each parameter to be set so that the network yields a good output from each input. And what does this require? It requires training over a huge data set of samples. A huge data set. In our case, training occurs for the chaotic double pendulum. It takes a long time to train the neural network to predict where things are going to be in the chaotic double pendulum. And the number of training samples there is in the millions, and the training time is about 8 hours for that. So what happens in the training? The neural network receives a sample input along with its desired output, and then it tunes the parameters so that close to the desired output is attained across the large number of samples that you input. So what happens after tuning is that we know that the neural network does a good job of giving a good output for each input that is part of our training set. Now, the miracle of the neural network is that it's able to extract patterns and important features from that training set and apply it to inputs that are not in the training set. So when we give the neural network an input that lies outside of the training set, it gives us a very good response for the output. In our case, we're going to use a continuous learning paradigm that's depicted by this graphic here. So we'll start on the green arrow here. So what happens is that we start by giving the neural network a sector or sectors of the pendulum configurations. So what is a sector? A sector is just those discrete points along the pendulum pathway that we saw before. We choose 16 discrete points. Each of those discrete points are successive pendulum positions on a single isolated trajectory. We may want to, when we train for a single trajectory, we give it one sector along that one trajectory. We also train across multiple trajectories, so we give it many sectors. Our sectors are generated by a Python ODE solver. Recall that the pendulum can be modeled by mathematical equations, and this ODE solver solves those mathematical equations, then feeds the results into the neural network as inputs into the neural network. And next, we go ahead into the training phase. The training phase is there so that we can tune the parameters as we get new data. So all those parameters, we're trying to match the input to the output. New data is coming in, so the parameters need to be tuned to incorporate this new data. And this is done within a software package called TensorFlow. To train a neural network requires extremely computationally intensive algorithms. These algorithms have been known for about 60 years now. This is nothing new, and yet neural networks have not been popular until recently. Maybe they've gained more popularity within the last 20 years. The reason that they've gained popularity is because of advances in hardware. To tune the parameters, as I said, it is computationally intensive, and it helps if you have a parallel processing capabilities. The new hardware, and specifically the GPU, has these capabilities, and that's what allows us to be able to tune a neural network now. TensorFlow, which is put out by Google, is a software package that sets up your neural network on a parallel processing environment such as the GPUs. And finally, once the parameters are tuned, we get some output, and we store that output into a database. In my case, I stored it into a MySQL database. And we come back here and get new data and repeat the cycle. Now, I do display the output, but not in this cyclic manner. Once the neural network has completed its training and all the data has been transferred to the database, I can go ahead and query the database and get results and then plot those results. So let's go ahead and look at some plots. For this first set of results, what I've asked the neural network to do is to train across 8 different trajectories running from a low energy to a high energy trajectories for the single pendulum. What you're looking at in this picture is the results after simply one training step on a low energy case. What you see is the blue pendulum, which is the true pendulum. That's the actual data that's being fed in. And this little red thing right here is the neural network output. It's orange, not red. It's the neural network output at any rate, and it looks terrible. It doesn't even know it's a pendulum. So let's see what happens after training is complete. And comparing the image on the left with that on the right, it looks completely different. Now the neural network has been trained. The neural network is tracking the true trajectory very well. It's a very simple case. So if they were in the juniors competition, they'd certainly take it. It looks like a perfect 10 there. Let's see what happens for a little bit more complicated case, higher energy output. And what do we see here? Once again, the initial case is looking extremely poor. The original pendulum is swinging around completely, doing a 360-degree swing, and the neural network is totally clueless, doesn't even know it's a pendulum. So let's see what happens after 10,000 training iterates. And okay, things are looking a little bit more promising. It's looking better. You can see that it's not a perfect track yet, but it's not doing too bad. There's this wobble at the top that you can see there, and as it comes down, the true pendulum comes down, the neural net is also coming down at a slightly different rate, and it's not picking it up perfectly, but it's certainly doing much better than the case on the left, where it's totally clueless. Let's have a look at it on its own so that we don't get any interference. And there, once again, we see, okay, not perfect, but more promising. Now let's go to the final stage after complete training. I believe this is after 1 million training sessions, and look what's happened here. The true pendulum and the neural network are in perfect sync with each other. This is a perfect 10 once again. And what does this demonstrate? This demonstrates that the neural net is able to learn behavior across many different initial conditions, across many different possible configurations of the single pendulum at a single time in one training session. So if you fed this some arbitrary initial condition into the true pendulum, the neural net would be able to follow it. This is quite promising and quite a nice result. Let's now go right to the most difficult case and look at that double pendulum that we earlier saw. Okay, for brevity, we'll jump right to the most complex case, the chaotic case of the double pendulum. Let me just say for completeness, however, that we did do the simple case, the case where the double pendulum was in quasi-periodic motion, and we were able to score a 10 on that one as well in relatively few training sessions. For the double pendulum, we did not attempt to run a training session across multiple trajectories. We only did one trajectory at a time. And what I'm going to show you right here is the most complicated one, the chaotic trajectory. And here's how we start off. As expected, the initial training session, after one training session, the neural network is clueless, doesn't know it's a double pendulum, can't follow the actual pendulum at all. Nothing surprising here. So let's see what happens after a few training sessions. In fact, after 15,000 training sessions. That is, we've gone through that cycle that we discussed on a previous slide 15,000 times. And let's see what we're looking like now. So here's what we got. Not perfect. We're certainly out of sync here, but it's looking a lot better than it looked before. And let's look at where we're at after 15 million training sessions. That's 8 hours later, after going through the entire cycle 15 million times. And we're not at a perfect 10. Let's close this one off. Never got to a perfect 10 on the double pendulum, but not bad. Not bad. The results are promising. Maybe with more training we could get to the perfect 10. The metrics of the neural network continued to improve at a very, very slow rate by the time we hit 15 million, but there was still some room for improvement. I just ran out of time here, and this is what we got. So this is the final result. Let's say it's not a 10, depending on who's judging it. Solid 7, maybe even an 8. Might be able to get to a 10 with more training. So let's wrap things up and see how we progressed on this project. At the start of the project, I was looking just to develop a framework for future testing. I didn't anticipate being able to design a successful RNN. All I wanted was to be able to put in place the components that would be necessary to test different RNN designs on dynamical systems. So what's required in order to do that? Well, we have all the components that are necessary. For dynamical systems, we'll need to generate the time series. So we have a Python ODE solver that generates the time series. We need to be able to design and configure a network. So we have that component in there as well. There are two possibilities in our program. You can either design your own neural network, or you can plug in a pre-designed component from TensorFlow. I did do just that. There's a design component for RNNs called LSTM. This is standard and used in many different applications. It's not specifically designed for dynamical systems though, and the neural network that I configured had yielded better results than the results from the LSTM. This isn't too surprising. If we tried to use the neural network that I designed on applications that the LSTM works well on, the neural network that I designed probably wouldn't be as good. Next, we have a Python interface to TensorFlow, which allows for training of the parameters. And finally, once everything's trained and you get an output, we have an interface to a database, MySQL, and then a process for graphically displaying results. So all the components necessary for future testing are in place. So where do we go from here? On a personal note, where do I go from here with this project and RNNs in general? Where are they going? What direction is it taking? So this project, I hope to continue. What directions could I take with it? Well, I can test more neural network designs. See that there are other ideas that I didn't have time for, and I can see how they work against the current design that I have. I'd like to be able to get that 2D pendulum down, move it from the 8 to the 10. I'd also like to look to increasing the dimension of the dynamical systems. Right now my configuration space is only 2 dimensions, and dynamical systems of interest come in much higher dimensions than just this 2D pendulum problem that we've been looking at. Another thing that I'd like to be able to do is to introduce a control into the problem, or into a dynamical system, so that I might be able to train the control to guide the system where we might want to take it. Those are things that I'm looking to do in the future. What about RNNs in general? Well, what direction are they taking? Well, I think that they can go toward highly complex dynamical systems. One example is the weather, where solving the full set of equations is difficult. We know the equations that guide the weather very well, but there are a coupled set of equations that include radiation, that include fluid dynamics, they include atmospheric dynamics as well as oceanic dynamics. They include cloud coverage and a lot of in topography as well. Just many complexities that make it very difficult to describe and solve the full set of equations. It's possible that using techniques similar to what I'm investigating and others as well, that we'd be able to go ahead and just plug in the data of weather from the past and let the neural network determine how the dynamics operate on its own. Another example is bird flights without equations. I don't know if we know the equation, if anyone's written down the equations of motions for a bird, for example, and how it responds to different wind patterns and how it guides itself. But it's feasible that we could throw in enough data into a neural network so that the neural network could figure out the flight of a bird without using any equations. In the area of art, we have music and artwork is already possible. You can look into the internet and find RNNs that have been designed to create both paintings and music. They do a pretty good job. I'm no expert or connoisseur of art, but I do like the productions from the neural networks. Now, there are no neural networks that I know of that are generating moving 2D and 3D images. Movies for a 2D screen or potentially 3D movies for these new Google goggles and other type of devices which are going to render reality in 3D. What is preventing us from doing these things now? I think that the biggest roadblock is processing power. In order to be able to do these things, we'll have to train neural network with millions of parameters in it, and we'll have to be able to set millions, maybe hundreds of millions of parameters, and that's going to take a lot of computational power. So as that computational power becomes available, we'll be able to do these sorts of things with our neural networks. So that concludes my presentation, but I'd like to end on a little bit of a personal note. This class has been a great experience for me. I'd like to thank Professor Huang. He certainly displayed a great deal of expertise during our class time. He was very patient in answering our questions. Even when we were off the mark, he made the questions hit the mark. He also had a sound understanding of the students' needs and addressed them very well with the material that he chose. I think he went above and beyond his call of duty. I'd also like to thank all of my classmates. It was an intelligent, imaginative, and knowledgeable bunch. I certainly learned a lot from your participation, and thank you all, and hope we have the chance to cross paths again in the future. Thank you.